Good morning, guys. Okay, in previous lecture we started our truss problem. This problem we have started in our previous lecture. Now in this lecture we will construct our global stiffness matrix for this truss element. Actually in previous lecture we determined our elemental stiffness matrices for this first element, second element and third element. This is the truss structure. Actually in examples they have mentioned all the things. In previous lecture we have determined by using all the parameters. First we constructed the table for this L length, then theta value, then small l means it is nothing but equal to L is equal to cos theta, M is equal to sin theta, then L square, Lm, M square. Then by using and actually these values we have determined all these values for each element. Okay, then by using this constructed table we determine our elemental stiffness matrix for each element. This is for first element, this elemental stiffness matrix is for first element, this elemental stiffness matrix is for second element, and this third elemental stiffness matrix is for this third element. Okay, so this is your first element, this is your second element, and this is your third element. So in previous lecture we have constructed elemental stiffness matrix. Now in this lecture we will construct our global stiffness matrix by using these three elemental stiffness matrices. Okay, so as we know that for truss element at each node there must be two displacement in horizontal direction as well as in vertical direction. So suppose this is node 1, so there are two displacements. In horizontal direction u1 is a displacement, in vertical direction v1 is a displacement. Similarly at node 2 u2 and v2, similarly at node 3 u3 and v3. So at each node there are two degrees of freedom. So as we know that what is the order of the global stiffness matrix? So order of the global stiffness matrix will be equal to number of nodes into the degrees of freedom at each node. So as there are 3 nodes, 3 into n is equal to 3 into now number of degrees of freedom at each node. Here there are 2 degrees of freedom at each node. So this order of global stiffness matrix will become 6. Okay. So the 6 by 6 matrix should be there. Okay, so this is the global stiffness matrix. Okay, now we have written our rows and columns here. So first, second, third, fourth, fifth, sixth. So for first node u1 v1, for second node u2 v2, for third node u3 v3. Similarly, for first node columns are u1 v1, for second node columns are u2 v2, for third node columns are u3 v3. Now we will construct our global stiffness matrix. Okay, so first this is the elemental stiffness matrix. Now this elemental stiffness matrix, the connectivity of this elemental stiffness matrix is in between u1 v1, u2 v2, because this first element is the connectivity of this first element is in between node 1 and node 2. It means between u1 v1 and u2 v2, means u1 v1 u2 v2 rows and u1 v1 u2 v2 columns. So we need to write down these elements over u1 v1 u2 v2 rows and columns. Okay, so this is your elemental stiffness matrix for first element. So we are writing this for elemental stiffness matrix between the connectivity of u1 v1 u2 v2 rows and u1 v1 u2 v2 columns. Okay, so 375. So we will write 375 0 minus 375 0 0 0 0 0, then minus 375 0 375 0, and last is 0 0 0 0. Okay, so in this way we have written our first elemental stiffness matrix over this global stiffness matrix between the connectivity u1 v1 u2 v2 and u1 v1 u2 v2 columns. Okay, so similarly now we will write our elemental stiffness matrix for second element or global stiffness matrix. Okay, so this second elemental stiffness matrix, connectivity of this second elemental stiffness matrix is in between node U2V2, means actually this connectivity is between node 2 and 3. So the displacements vary from U2V2 and U3V3. So third, fourth, fifth and sixth rows as well as third, fourth, fifth and sixth columns. Means this will vary from U2, V2, U3, V3 rows and U2, V2, U3, V3 columns. Okay. So we need to place this matrix over this. It will start from this point, U2 rows, U2 column, and it will end at this point. So we need to place this matrix as it is. So 353.5. So it will become plus 353.5 minus 353.5 minus 353.5 plus 353. So similarly, now U2 column, U2 rows. Now U2 column, U2 rows means this is your matrix. So second minus 353.5 plus 353.5 plus 353.5 minus 353. Then minus 353.5. This element 353.5 minus 353. Last row 353.5 minus 353.5 minus 353.5 and last element 353.5. Okay, in this way we have written this second elemental stiffness matrix over these positions. Okay, so connectivity of this second elemental stiffness matrix is in between node 2 and 3. Node 2 and 3 means between U2V2 and U3V3. As at each node there are 2 degrees of freedom, so connectivity is in between U2V2 and U3V3. Now finally, last elemental stiffness matrix, third elemental stiffness matrix, we need to map this elemental stiffness matrix over this global stiffness matrix. Now the connectivity of this elemental stiffness matrix, this connectivity is in between node 1 and node 3. Okay, it means the connectivity is in between rows U1V1, U3V3 as well as columns U1V1, U3V3. So U1V1, U3V3, U1V1, U3V3 columns. So we need to place these elements over U1V1, U3V3 rows as well as U1V1, U3V3 columns. So what are these? So we need to place this U1V1, U3V3 means U1V1, U3V3. Similarly, U1V1, U3V3. Then finally, U1V1, U3V3 and U1V1, U3V3. In this way, we need to map these 8 elements over this global stiffness matrix. So this is U1V1 353.5 plus 353.5. Second 353.5 plus 353.5. Now this is U1 row but U3 column. So U1 row but U3 column. Here is this value. So minus 353.5. Similarly, U1 row and V3 column. U1 row and V3 column. So this element should be there. So minus 353.5. Now V1 row and U1 column. V1 row and U1 column. So this is the element. So 0 plus 353.5. Now V1 row, V1 column. V1 row, V1 column. Here is the value plus 353.5. Now V1 row and U3 column. V1 row and U3 column. So here is the value minus 353.5. And similarly V1 row and V3 column. V1, this is the V1 row and V3 column. So this is the minus 353.5. Now next is what? U3 row. So we will come at this row, U3 row and U1 column. So U3 row, U3 row, U1 column. Similarly U3 row, U1 column. So this is the value. So this is nothing but minus 53.5. Similarly U3 row, V1 column. U3 row, V1 column minus 53.5. Then U3 row, U3 column, U3 row, U3 column. Look, this is U3 row and U3 column. So the value should be at this one. So this is nothing but your 353.5. So plus 353.5. Finally, U3 row and V3 column. So this value we need to place. So U3 row and V3 column. So it should be placed there. So plus 353.5. So plus 353.5. Now next, finally we need to map this V3 row. Okay, over there. So V3 row, U1 column. So this value should be here minus 353.5. Similarly, V3 row, V1 column. V3 row, V1 column. It should be there minus 353.5. Now V3 row, U3 column, V3 row and U3 column. So this value it should be there plus 353.5. Similarly, V3 row, V3 column. So we need to place this value. This is at position V3 row, V3 column. So V3 row, V3 column. So it should be there. And this value is plus 353.5. Okay, so in this way we have placed all these elemental stiffness matrices elements over global stiffness matrix. Okay, so now just do the simplifications you will get. So okay, so here finally you will get the global stiffness matrix as these values there. So this is 6 by 6 matrix. So we need to write down this K matrix here. So K is equal to U1, V1, U2, V2, U3. U1, V1, U2, V2, U3, and V2. Okay. So 375 plus 353.5. So what is the value? 728.5. This simplification is 728.5. 728.5. Then we will go from column to rows. Okay, so 0 plus 3 is 353.5. 353.5 minus 3, 75. Then 0. Then 353.5. Then minus 353.5. Okay. Now V1 rows. 0 plus this 353.5. 0 plus this 353.5. 0, 0, 0, 0, minus 353.5. Then minus 353.5. Then U2. Okay, U2 is 37 minus 375. 0. 375 plus 353.5. 728.5. This minus 53.5. Then minus 53.5. And last one is 3.5. Okay, then V2 0 0 minus 353.5 plus 353.5. So minus 353.5 plus 353.5. Okay, V2 was 353.5 minus 353.5. 353.5 minus 353.5. Then U2. So U2. Sorry, U3. Up to this we have covered. Now minus 353.5 minus 353.5 minus 353.5. So minus 353.5 minus 353.5 minus 353.5, then 353.5, 353.5. This 353.5 into plus 353.5. It is 707, I think. 707. Then minus 353.5 plus 353.5 is equal to 0. Then finally V 3 minus 353.5 minus 353.5 minus 353.5 353.5 minus 353.5. Now this value, look at this, minus 353.5 plus 353.5. It is equal to 0. 353.5 plus 353.5, 707. So this is the global stiffness matrix. Finally, you will get this as a global stiffness matrix. So this is your global stiffness matrix. Okay. Finally, these are the values. Okay, so now next step is what? Next step is what? Write down the force and displacement relationship. So as we know that force and displacement relationship with the help of global stiffness matrix. Okay, so this is the force and displacement relationship. Okay, so here as we know that there are 6 displacements and 6 forces. As this is our example. Okay, this is the example actually. So this is first node. Actually, roller support is mentioned. And 150 kilonewton. Force of 150 kilonewton is applied. 1, 2, and 3. So we know that at node 1 there are displacements U1, V1. Similarly, there are forces F1x in horizontal direction, F force acting at node 1 in vertical direction. Similarly, at node 2, U2 is the displacement in horizontal direction and V2 is the displacement displacement in vertical direction. Similarly, F2x is the force acting at node 2 in x direction, and F2y is the force acting at node 2 in y direction. Similarly, at node 3, U3 is horizontal displacement and V3 is vertical displacement. Similarly, F3x, this is the force in x direction, and F3y, this is the force in y direction at node 3. Okay. So, this is the free body diagram of the structure. Now, we need to construct the force and displacement relationship with the help of global stiffness matrix. So by using these forces and displacements, we can construct our global stiffness, we can construct our force and displacement relationship. So how to construct? So we know that on LHS side there must be a force vector. LHS side there must be a force vector. So this force vector is nothing but F1x, F1y, F2x, F2y, F3x, F3y. Okay, so this is the force vector on LHS side. Okay. Similarly, for this, we need to construct our displacement vector. So displacement vector is given by using these three nodes, we can construct our displacement vector as U1. For first node, we know that two displacements, U1, V1. For second node, there are two displacements, U2, V2, and for third node, there are two displacements, U3, V3. Okay, so in this way, you can construct your force and displacement relationship by using this global stiffness matrix. Now next is what? As we have constructed our force, we have written this global stiffness matrix in the form of force and displacement relationship. Now next step is what? Apply the boundary condition. Now this is the apply the boundary condition. This is the main step in this example. So how to apply the boundary conditions? Now, so look at this first node. What will be the situation? For this first node, it is fixed in both directions, in vertical direction as well as in horizontal direction. So this node 1 it is fixed one. It is fixed one in horizontal as well as in vertical direction. So due to this, we will get boundary conditions here as U1 and V1 is equal to 0, because this node 1 it is fixed one in horizontal as well as in vertical direction. This is a fixed one, and due to this there will not be any displacement or any movement of this node in horizontal as well as in vertical direction. Now next is what? Now look at this second node. Okay, this is a roller support, and due to this roller support, there will be some type of displacement. It will be occurring in horizontal direction. Means there must be some displacement due to this roller support. There must be some displacements. There will not be some displacements in horizontal direction. Why? Because of this roller supports, you will get some displacements in horizontal direction. So U2, there must be a U2 value. We need to find out. So it is unknown value. But what about V2? Actually, this is due to this roller supports, there will not be any displacements in vertical direction. Okay. So due to this reaction, actually this roller support reaction, there will not be any movement in vertical direction. So this V2 must be equal to 0, and U2, actually there must be some displacements in horizontal direction due to these roller supports, because this is a roller support, so this node it will move in horizontal direction. So U2 must be there and it is unknown. We need to find out this U2 value. And at third node, U3 it is also, actually there is no any type of support here. So we need to find out U3 as well as V3. We need to find out U3, V3 as well as this U. And this U1, V1 is equal to 0 and V2 is also equal to 0. So put these boundary conditions in this equation. So you will get U1 is equal to 0, V1 is equal to 0, V2 is also equal to 0. And these three parameters are unknown. Okay. Now, this is for your displacement boundary condition. Now, force boundary condition. We need to apply the force boundary conditions. As we know that at node 3, at node 1, there are two reactions, R1y and R1x. Means R1x and R1x, it is in horizontal direction, R1y, it is in vertical direction. There must be two reactions at this node due to this Victor support. Similarly, at this node, there is only one reaction which is acting vertically upward or vertically downward due to this roller support. Due to this roller support, there will not be any type of force in horizontal direction. Okay, this horizontal direction is not restricted. It means there will, and at this node, a horizontal force it is not given, but vertical force, it is nothing but this is the roller support reaction. Okay, so horizontal force it is not given, so F2x is equal to 0. We can take this F2x is equal to 0. And F2y it is nothing but equal to your R2y. Okay, F1x is nothing but equal to your R1x, and F1y is nothing equal to R1y. Means support reaction in horizontal direction, support reaction in vertical direction. Because at this node there must be two reactions in x as well as in y direction. But at this node there will be only one reaction in vertical direction, and it is nothing but your R2. And in horizontal direction there will not be any type of reactions due to this roller support. So this F2x and also the any type of force is not given at this node, so it will become equal to 0. So F2x is equal to 0, F2y is equal to R2. Now at third node, a vertical force is given. It means F3y is given and it is equal to nothing but minus 150 kilonewton. As all the parameters we have taken in kilonewton per mm square, kilonewton, so we need to take this F3y, it is also in 150 kilonewton. Okay, so F3y it is given minus is what? Because it is actually in downward direction, so we need to take it as a minus. Now F3x is not given, so we need to take it is equal to as 0. It is not given, it means it should be equal to 0. So put these force values also. So for F1x is nothing but R1x. So this will become your R1x. F1y means R1y. F2x, now look, F2x is equal to 0. So F2x it will become 0. F2y, look, this F2y is nothing but your R2y. This vertical support or support reaction. R2. Now F3x is equal to 0. F3x is equal to 0. Now F3y is equal to minus 150 kilonewton. F3y is equal to minus 150. Okay, as actually we have taken all these values in kilonewton per mm square or kilonewtons, so we need to take this value also in kilonewtons. Okay, so 150 kilonewton. So now, as we have applied our boundary conditions, now next thing is what? Apply the elimination approach. So we need to apply the elimination approach. So as we know that which displacement values are 0, eliminate these rows and columns from these global sequence matrix and find out the displacements by using your remaining equations. So here u1 is 0, it means eliminate first row and first column. So eliminate first row and first column. Similarly, v1 is equal to 0. It means eliminate v1 row and v1 column. So v1 row and v1 column. Next is what? v2 is equal to 0. So eliminate v2 row and v2 column. So v2 row. So this is your v2 row and v2 column. Okay. So in this way we have eliminated u1, v1 and v2 rows as well as columns. Now the remaining equation we will write here the remaining equations. So remaining equations are what? Okay, this is also eliminated, this is also eliminated, and this is also eliminated. So remaining equations is what? Okay, so here we will write this third equation is remaining. Similarly, this fifth equation is remaining, and similarly this sixth equation is remaining. So write down these equations. These equations are written as 0, 0, 0, minus 150, 0, 0, minus 150 is equal to 728.5, 728.5 minus 3.5 minus 353.5, 353.5, 353.5. Then minus 353.5 here, minus 353.5, this value is 707 and this value is 0. Then 353.5, 353.5, this value is 0 and this value is 707. In this way you will get the eliminated. You will get this remaining 3 equations. This is on this equation u2, u3 with u2, u3 and u3. So this is your these are the 3 remaining equations 0, 0, 1 minus 150, 0, 0 minus 150, then this minus 728.5 to 3.5, 728.5 to 3.5, then minus 3.5 to 0, to 0, and this 3.5, 0, 7, and into u2, u3, u2, 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 u3 and v3. Okay. So solve these 3 equations. You will get u2, u3 and v3 values. Okay. So by solving these 3 equations, you will get u2, u3 and v3. So how to solve this equation? So by using Gauss elimination, or you can directly solve it by using your calculus in 3 unknown parameters. In your calculus, there is an option in equations to find out 3 unknowns by using 3 equations. So you can directly put all these values in your calculus and you will get the final answer as the displacements. By using your calculus, you will get the displacements as, so these displacements you will get equal to, so you will get u2 equal to, by solving these 3 equations in your calculus, you will get simply u2 is equal to 0.2m, u3 is equal to 0.1 mm, and u3 is equal V3 is equal to minus 0.312. Okay, so in this way you will get U2, U3 and V3 values. Now first equation was find out the displacement values at each node. Now next is what? Find out the stresses in each element. So to find out the stresses in each element, we know that the formula. So sigma 1 is equal to, this is formula, E1 by this capital L1 into this matrix minus L1 minus M1 L1 M1 into displacements related to your first element. Actually this first element, connectivity of the first element is in between node 1 and 2. So at node 1, U1 V1 is the displacement, at node 2 U2 V2 is the displacement. So displacements related to first elements are U1 V1 U2 V2. So by putting L1 M1 L1 M1, it means we have constructed first table. Okay, to find out the values for element. L is nothing but cos theta, M is nothing but sin theta. So we have actually determined this L1 M1 L1 M1 for element 1. So here sigma 1 will become E1 by L1. This L is nothing but length. This small L is nothing but cos theta. So cos theta and sin theta values. So this row into this column you will get the sigma 1. So put all the values of this sigma 1. You will get all the values of these parameters. You will get sigma 1 as sigma 1 equal to, do these calculations in your home. Sigma 1 is equal to minus 0.05 kilonewton per mm square, because U1 V1 U2 V2 all values are known. Similarly sigma 2, so for sigma 2 change is what? E2 L2, this L2 M2 L2 M2 values are sin theta and cos theta values for this element 2. So here the change is what? The connectivity of this second element is in between node 2 and node 3. So for node 2 U2 V2, for node 3 U3 V3. So these displacements will be U2 V2 U3 V3. So put all the values, you will get sigma 2. So sigma 2 values equal to, you will get sigma 2 as 0.053 kilonewton per mm square. Then finally sigma 3. So for sigma 3 the changes will be E3 by this L3 here, L3 M3 L3 M3. So this connectivity of this third element, it is in between node 1 and node 3. So node 1 it is nothing but U1 V1 and node 3 is nothing but U3 V3. So put all these values, you will get sigma 3 as 0.053 kilonewton per mm square. Okay, so in this way you will get sigma 1, sigma 2 and sigma 3. So this, please do these calculations at your home. Okay, you will get these values. If you didn't get, you will not get these values, then you can message me. I will solve this example. Actually this is simple one. This simple step. This first row into this first column. So you will get this simple values also. So now next is what? Reactions. We need to find out these reactions. R1x, R1y and R2. So to find out R1x, we need to solve this first equation. Means R1x is nothing but equal to this value, this row into this column. So as we know all the values here now, so multiply by this row to this column, you will get R1x. So R1x, by using this first equation, R1 you will get the R1x as R1x is equal to 0, then you will get R2y, R1x as equal to 0, then you will get R1y as equal to 75 kilonewton and R2y is equal to also 75 kilonewton. So from this, as we know that at node 3, 150 kilonewton is acting downward, and at these two supports, this is R1y 75 kilonewton, this is R2y 75 kilonewton. So this force is balanced by these two reactions. So our answer is correct. Okay. So in this way you can solve the truss problem. So these problems can be asked for your end semester examination for 12 to 14 marks. Okay. So we conclude our lecture here. Thank you.